Hi there. Hi, everyone. My name is Mia. I'm one of the producers of TWiML Fest. We're super excited to have you here. This session is Deep Learning in Medical Imaging, moderated by Mehul Sampat, Principal Architect at Bioclinica. And we have several wonderful guests here. You'll hear from Stefan Borstelman, Siva Rajaraman, and Anthony Reyna. Before we get started, I'd like to thank our sponsors for their support of TWiML Fest and today's session. And also just a quick note, today's session is hosted on Zoom, so please take a minute to note the location of the chat, and please feel free to send any questions throughout the session via the chat. We'll be monitoring and having the Q&A at the end of the session. And I'd like to turn it over to Mehul. All right, have a great one.
Okay, thanks, Mia. Okay, let me share. Hello, everyone. Welcome to this session on deep learning in medical imaging. Let me quickly share my screen. Okay, can someone tell me, do you see my slides?
Yep, you're good.
Yes, we can see you.
Okay. Okay, thank you everyone for attending this session. The session is deep learning in medical imaging, and we have a distinguished set of speakers in the session. I just want to just a few logistics. So we'll talk about we'll have the presentations, and like as Mia said, we'll have the Q&A at the end. So please put your questions in the chat. Okay, so here's what I'm going to do. I'm going to give you a very short overview and talk about various aspects of deep learning in medical imaging. So this is a very vast topic. So I want to give you like a global overview, and then our speakers will dive into technical details. Okay, so let me get started. So the first thing is why all this interest for deep learning methods in medical imaging? What's the motivation? Okay, so in medical, for accurate diagnosis, it depends both on image acquisition and image interpretation, right? And image interpretation is typically done by medical experts, which are radiology specialists, for example. Okay. So there are multiple articles that almost 2/3 of the world population lacks access to radiology specialists. Okay, and this disparity is truly astonishing. So an article reported there is a single hospital in Boston has 126 radiologists, but a population of almost 43 million in Kenya has access only to 200 radiologists. So that's one big aspect of the motivation. And then the second is that with deep learning methods, you can help reduce diagnostic errors and also help improve efficiencies. So the next item is we're going to look at some applications and then look at how these compare to human experts, and then finally where we stand now in comparison to what is already FDA approved and being used. So I'm going to talk about two general applications to give you an overview. So the first one is medical image classification. So here our objective is to classify each image into a particular category and then measure the performance of your deep learning algorithm by comparing the algorithm output to some ground truth category. And our next speaker will talk about the metrics that will be used. So I don't want to go into metrics in my session. Okay, and it's basically for this application, you follow the same standard deep learning guidelines. That is, use non-overlapping training and testing data sets, and so on. And in this particular example, what I've done is I've tried to get examples where you can easily reproduce the example. So at the bottom of the slide is a link. So after the talk, I'll share these links. But basically, you could just go to this Python notebook, open it, and create these same images. That's how I created this. It's from a popular free medical training image data set, and you can also train your algorithm for yourself using this notebook. Okay, so throughout my talk there will be numerous links like this, which can help you get started on trying these applications. Okay. So the first application was image classification, and yeah, here I had classifying images into categories such as different anatomies like hand, chest X-ray, and so on. But there are numerous papers, whether it's like saying, okay, is there a fracture in the image or not? Okay, so, or is there some other abnormality? Okay, so that's the general idea. Okay, the second main big application is medical image segmentation. So just to be complete, yeah, segmentation is the process of dividing an image into meaningful components. Here on the left, we have an image of a brain with a tumor, and on the right, we have the manual segmentation of different components of this tumor. Okay, and again, this one to reproduce this experiment and these results, you can access this GitHub repo. Basically, what I did is I was reviewing I've reviewed more than 100 papers and blog posts, and I try to find things with which you can with which the message is passed very quickly, and you can try it out yourself. Okay. So here is one example of one image slice. So you have the manually created ground truth and the algorithm output on the right. Okay, but typically in medical images, you don't have a single image like your other computer vision applications. You may have a stack of images because you are imaging the brain from the top to the bottom. So you would typically have like a stack of images, and then you have your segmentations on each slice. Yep. So this is just showing that. And I showed you the brain tumor example, but this is a very active area. There are numerous online segmentation challenges. This is from a website called Medical Decathlon. Here we have segmentation of pancreas, hippocampus, lung tumors, liver tumors, all sorts of various different applications where there's a lot of interest in academia and industry. Okay, so now we've talked about some applications, right? Okay, so we can run these algorithms, do some computations. How do these perform compared to human experts? Okay. So there's a lot of interest in this, and the take-home message is that that these performance of these deep learning methods are similar to healthcare professionals. Okay, and there's a recent paper by Liu et al. Where they compared more than like 58 studies with human readers and 100 studies with deep learning models. Okay, so I know that this is a little busy slide with metrics, but that's why our next speaker is going to talk about metrics. So we will get more details about what these metrics mean exactly. Okay. Lastly, okay, so we have a lot of interest in developing algorithms. We have seen these compare well to humans. So before we can start using them in the clinic, they need, these algorithms need to be passed through FDA approval. So my last two slides are, okay, what are the FDA approved algorithms and where we stand? So on the left hand side is the timeline starting from 2016 to 2020. And on the right hand side is the domain. So for example, cardiology or emergency medicine or neurology or radiology. Okay. So there are different applications such as detection of stroke on CTs, detection of diagnosis of sleep disorders. So that would be like a classification example. And there's also a wonderful one on triage. That is when people come into the emergency room, can you say, okay, who should get priority? Which patient should be given priority? Okay. As you can imagine, this is a very active and hot topic. And just earlier this year, before everything shut down in Feb 2020, the FDA had a workshop titled "The Role of AI in Radiological Imaging," and they talked about various things like such as, okay, how can AI be used to automate some components of the radiology workflow? And if you do this, what are the risks and benefits of this? And what are the best practices for validation? It's a 2-day. It's such a there's so many details there. that they have a they had a 2-day workshop, and all the talks and PDFs are available online. Okay, so I will stop. So that's my overview. Okay, so that's what applications are there and what's currently available in the what's currently available and approved by the FDA. Okay, so I'll stop sharing, and our next speaker is Dr. Stephen Bolstenman. He will talk about beyond ROC methods to judge real-life performance of algorithms. Okay.
Thank you very much, Mehul. I'm gonna let me switch to my screen. And are you seeing my slides, or are you seeing my slides and my notes?
Only your slides.
Fantastic. So, hello, everybody. I am Stephen Borstelman. I am an interventional radiologist who has, for some crazy reason, decided to be really interested in deep learning and machine learning. My talk to you today is Beyond ROC, Methods to Judge Real-Life Performance of Algorithms. I have nothing to disclose. I don't have any financial interest in the systems that I'm discussing in this talk. I do own stock in Google. So I'll give you a brief history of deep learning in radiology. 2015, nobody knew anything about it. In 2016, we all found out that there was something called TensorFlow, and you use that with Python, and you fed the thing data, and stuff popped out. In 2017, Andrew Ng and Pranav Rapunjkar from Stanford used the NIH chest X-ray 14 data set to develop a DenseNet 121 that they claimed performed as well as a radiologist in the identification of pneumonia. Myself, Paras Lakhani, and Luke Oakton-Rader said, hey, wait, not so fast. And it generated a great deal of discussion, and radiology at that point decided to wake up and pay attention to AI. 2018, we had fantastic results with proprietary data sets and proprietary algorithms, which were all secret, and a lot of hype, including some companies that were so secretive they wouldn't even tell you what they were doing. Bring that forward to 2019, where we have 150 companies and FDA approvals of AI algorithms are going forward. So the question is, as always, how to separate hope from hype? And the answer is science and statistics. So I'm going to show you a 2x2 confusion matrix, and this is the 2x2 matrix on the right side of the screen. Consider a test for coronavirus. You think you might have coronavirus, you go get tested. Well, if you have coronavirus and you test positive, good, the test worked as it was supposed to work. If you don't have it and it tests negative, that's also good. But what happens if you test positive and you really don't have it? Well, we call that a false positive. It's a pain, it's annoying, but it doesn't necessarily invite a disaster. On the other hand, if you do have coronavirus and you test negative, that's a false negative, and that is generally more serious. And in medicine, false negatives are generally more worrisome than false positives. We evaluate the confusion matrix by classic measures of sensitivity, specificity, and positive predictive value. Sensitivity is how good the test is at finding the disease. Specificity is how good the test is at clearing you from having the disease, being truly negative. And positive predictive value is how likely are you to have the disease if you test positive. By the way, I know I'm speaking a little bit fast. It's because of the format. This is being recorded, so don't worry if you don't get it the first time. So since we're going to go beyond the ROC curve, we should talk about the ROC curve. And I've produced a ROC curve for you to see, and you saw that in Mehul's graphs earlier. So the ROC curve is a plot of sensitivity versus 1 minus specificity. Better is toward the upper left-hand corner. I have model A in yellow, model B in orange, and a purple line which has no predictive value. That's the random classifier. Model A lies completely outside model B and is said to dominate model B. Most people would consider model A to be a stronger algorithm than model B on the basis of this graph. You can also integrate the area under the curve, or the AUC of the ROC, and generally a larger number for that is also better. Advantages of the ROC curve is it's widely accepted. This is one of the things you're going to have if you decide to give an algorithm to the FDA. It allows you to compare algorithms visually. The AUC ROC is a single number statistic that also allows for comparison. And the ROC is prevalence invariant. Some disadvantages of the ROC is that high-performing algorithms tend to overlie each other. Some areas of the curve are trivial. You would never run an algorithm with a sensitivity of 1% and specificity of 99%. In situations where there's class imbalance, it can be misleading. And the AUC ROC is not a good measure of the performance of a system in a specific application, but its applicability across a range of operating conditions, and that's according to Powers. So Kin et al. Put out an interesting study a few months back where they used 3 different AI systems. Delft was a machine learning system, probably an SVM or a random forest, and Luna and Cure were both convolutional neural network-based models. They compared the 3 of them for tuberculosis detection in Nepal and Cameroon. And this is what they got in terms of an ROC curve. Take a peek at the operating area of the ROC curve, which is in the box. Very similar performance, and all of them cross each other. If you look at the ROC AUC, CAD for TB is a little bit lower at 0.92. Both CNN classifiers are at 0.94, but all of them are within 95% confidence intervals of each other. So this is the problem with ROC and AUROC. AUROC does not mean the proportion classified correctly. AUROC, you can also only compare on the exact same data set. And if there isn't any dominance, how can you decide which is better? I certainly can't tell off of the last image I showed you. So we can go to precision recall curves and average precision. Precision is just our old friend PPV with a different name, and recall is sensitivity. So better is towards the upper right-hand corner. Average precision is the integral under the curve of the PRC with some finer mathematical points. Advantages of the PRC is that it is useful for imbalanced classes. It gives you an alternative visual to an ROC. Some authors have suggested that PRC and average precision are more informative than ROC and AUC ROC for binary classifiers on imbalanced datasets. PRC can give you a sanity check because when you optimize ROC, it doesn't necessarily optimize PRC. And AP is another single measure statistic. Some of the disadvantages is that the PRC curves may not be smooth, and this may cause difficulty interpolating between points or calculating the AP. The horizontal baseline that's random changes as a function of class imbalance and the class ratio, and it's focused on the positive case. So here's a comparison of an ROC curve versus a PRC curve, and you see in graph A, the ROC plots, first you have 1,000 positives and 1,000 negatives. On the right, you have 1,000 positives but 10,000 negatives. I challenge you to find any difference between the graphs because they are the same. You have a perfect classifier, a very good classifier, the random classifier, and 2 classifiers that are less good. Compare that to the precision recall plots. In the balance case, there is some difference between the different algorithms, but they're fairly similar. But look at what a difference you have on the right when you go to 1,000 positives and 10,000 negatives in a 10-to-1 class imbalance. All of a sudden, those curves are substantially different. And this is what I'm trying to emphasize. Class imbalance is important. Don't take my word for it, okay? Take Ian Goodfellow's. He wrote the book on deep learning. Maciej Mazurowski made a number of articles that talk about the effects of class imbalance on classifier performance, and class imbalance does degrade classifier performance. So let's see if we can go beyond and get to something better. Accuracy is a common deep learning metric. We all use accuracy in training our deep learning models. The problem with accuracy is that high accuracy can coexist with poor performance for uncommon or rare cases with imbalanced data. The F1 score, or dice coefficient, is a common metric used in segmentation. It does address class imbalance, but it doesn't account for true negatives. Interestingly, it's the harmonic mean of precision and recall. So there are two statistics called informativeness and markedness that you may not have been exposed to before. Informativeness is simply sensitivity plus specificity minus 1. Markedness is PPV plus NPV minus 1. Informativeness is also known as bookmakers informativeness or Udin's J statistics. And that's possibly why it hasn't really taken off more, because it's kind of confusing where to find it in the literature. It represents how informed the tested system is about positives and negatives. It's basically congruent with a trader's or gambler's edge. If you're in fintech, think alpha. Markedness is a measure of how trustworthy the system's predictors are. It ranges from -1 to 1, with 1 being a perfect correlation, -1 an inverse perfect correlation, and 0 terrible. Interestingly, the AUC ROC is equal to informativeness in the select case of a binary classifier with a single threshold. So that preps the stage for the reason for this talk, which is the Matthews correlation coefficient. The Matthews correlation coefficient is a special case of Pearson's row. It yields a score from -1 to 1 with 0 in between. Again, 0 is terrible, 1 is great. It addresses class imbalance. It uses all 4 measures from our contingency table. And the MCC components are informativeness and markedness, and MCC is the geometric mean of these two. There are intrinsic biases that are present in the metrics that we use. Sensitivity and specificity are unbiased. Ditto for bookmakers' informativeness. But take a look at accuracy in the top right. It has a bias. PRC, precision recall, also has a substantial bias. F1 has a bias, but the least bias out of all these is the Matthews correlation coefficient. I put together some cases, balanced, imbalanced, and severely imbalanced. The bottom line is that I have 100,000 cases in severe imbalance. I can train a classifier with an accuracy of 0.998, but I have a Matthews correlation coefficient of 0.02. That's because the classifier will just ignore the one true positive you're trying to find and focus instead on the true negatives. Matthews correlation coefficient is helpful for telling whether you have a good system or not. Don't worry about calculating it. You can easily do so through the PyCom package. If you're an R person, Confusion Matrix, Caret, ROCR, and PrecRec packages are available for you. So recommendations for metrics. The basics are the ROC and the AUC ROC, sensitivity and specificity. For imbalanced data, I think it's reasonable to add precision recall and AP. But MCC may be one of the best and most underutilized measures of performance at a binary classification. We do need more experience with it to make that statement confirmed. MCC is particularly useful in the case where two evaluators or systems are being compared with no a priori reference. It's possible that we could start comparing apples to oranges through MCC. And as a practical conclusion, when dealing with imbalanced data sets, bookmakers' informedness is probably the best if you are only focused on positives, okay? But if you have to consider classification errors, then MCC arises as the best choice. With that, I'm going to thank you for your attention. You can find me on Twitter, which is where most people find me, as DRSXR, or my GitHub, or my LinkedIn. Thank you very much.
Thank you, Stephen. That was great. Great summary on all the metrics and MCC. Okay, our next speaker is Dr. Siva Rajaraman. He's a research scientist at the NIH, and he will give us a presentation on deep neural and ensembles for improved pulmonary detection and chest radiographs. Okay. Okay, we can see your slides. Yep.
Oh, you can see my slides, so thank you.
Yeah.
I was supposed to ask that. Okay.
Sorry.
Good evening, one and all. I'm Sivaramakrishnan Rajaraman. I'm working as a research scientist at the National Library of Medicine. Here at the National Library of Medicine, I'm working on research and development projects that apply computational sciences and engineering methods towards advancing life science applications. I develop machine learning, in particular deep learning models for detecting abnormalities in medical images, particularly chest radiographs. In today's talk, I'm going to discuss with you some of our works here at the National Library of Medicine that apply ensemble learning for improving pulmonary abnormality detection in chest radiographs. Before I begin, I wish to stress that the opinions are mine that result from my own research, and they do not reflect the views or policies of HHS, NIH, or NLM. As we all know, deep learning is the state of the art in image analysis and pattern recognition. Deep learning is a subset of machine learning that uses deep neural networks that are hundreds or even thousands of layers deep, and does automated feature extraction and classification as compared to the conventional machine learning methods. At present, deep learning is outperforming all conventional methods. The performance of deep learning is found to increase with the amount of quality data, and all the industry giants, including Amazon, Facebook, Microsoft, and others, are deploying deep learning models into their applications. Even the small and medium-sized companies are also deploying deep learning methods, but if you can see that there is a quality gap in the AI products just because of the amount of data available. While the industry giants have have access to lots of data, the small and medium-sized companies do have a restricted amount of data that suppresses the performance of deep learning models. There is always a challenge in applying deep learning to medical image analysis as compared to natural images. Natural images are available in abundance, whereas medical images are not. The first and foremost challenge is the limited availability of quality annotated medical imaging data. So it is easy to crowdsource the natural images and get annotations, but that's not the case with medical images. We need expert annotations. We need experts' knowledge about the problem under study to do the annotations. So there is a dire need to develop a massive amount of training data with expert annotations. And this is definitely a laborious, time-consuming task. The second challenge is the lack of standard models. Almost all the deep learning models that we use at the present are trained on ImageNet data, that is a collection of stock photographic images. There are around 15 million images belonging to 22,000 natural categories. But we don't have any dedicated model as of now exclusively for the medical data. The third challenge is data standards. It is very obvious that the data collected across institutions differ in their characteristics because of the difference in hardware, because of the difference in the sensors, the acquisition method, and other factors. So if you want to develop a robust and generalizable model, it is very important, or it is mandatory to collect a lot of data from several institutions and train these models to be highly robust and generalizable to real-world applications. The fourth challenge is the privacy and legal issues. because sharing of medical data is always a complex and difficult task. It is it's very important to keep away the personal identifiable information and the personal health information to maintain the privacy of the patients. And then this process by itself takes a lot of time, and it's also a very complex process. The fifth and the most important challenge is the explainability of the deep learning models. Most of the papers, as we see at the present, they all discuss about getting a very accuracy or very high performance at the quantitative level. But when it comes to explanation, most of these studies does not discuss or does not explain how these predictions are achieved. It's just because of the depth of these deep learning models, because they're extremely huge with several millions of parameters. There is an extensive, the weight matrices are very, very large as we go deep into the models, and this makes them unexplainable. So there is a need to explain these predictions in order to faithfully supplement clinical decision making, because if it's a natural images, even if some portion of the image is missing, for example, even if the tail of the snake is missing, it is still possible to classify the snake as a snake. But that's not the case with the medical images, because the region of interest, the disease region of interest, is very, very small. It may just span like 2 to 5% of the entire data. In that case, if that portion is lost, then it is very hard to differentiate an image showing an abnormality from a normal image. So under these circumstances, it is indispensable to explain the predictions of the model, not only at the quantitative level, but also the quality of the predictions. Now I'm getting into some of the terms that I use in my papers. The first term I would like to introduce to you is called the modality specific learning. All these times we have been using the ImageNet pre-trained models. These models are trained on natural images, as I told you before. But the transfer of knowledge from these ImageNet trained models to a medical domain is highly irrelevant. So what we thought of doing is to pre-train the entire model on modality specific data. For example, if I'm using this model for doing a chest X-ray based classification, I would like to pre-train this entire model to make these weight layers specific to the chest X-ray modality. It's because the visual characteristics of chest X-rays are completely different compared to natural images. The reason is they have a very highly localized ROI, as I told you before. And also there is a high degree of interclass similarity and intra-class variance. It's because, let us take, for example, tuberculosis. The disease manifestations for tuberculosis is not the same in all the chest X-ray images. They manifest differently in different images. Also, when you think about the, so that's what I say it's an intra-class variance. And also let us take, for example, classifying pneumonia from tuberculosis. There is a high degree of similarity because both pneumonia and tuberculosis may manifest as opacities in different distinct regions of the, in distinct regions of the lungs. So there is a high degree of interclass similarity. That may not be the case with the natural images. So the medical images are different from natural images in these aspects. And also when we do a conventional transfer learning, since the data is available in too small quantities, sometimes the transfer of knowledge is not reliable. The models are prone to overfit. So taking all these limitations into consideration, we thought pre-training the models on modality-specific data would improve generalization and also performance compared to using a conventional transfer learning model using ImageNet weights. The second idea is ensemble learning. Yes, obviously we all know that ensemble learning is always better when it comes to tackling the bias variance trade-off. The highly biased model will underfit because of the less complexity in the model parameters. The model may not be good enough to train on the data and it may not learn all the characteristics. So it is prone to underfitting. When it comes to high variance, the model is too complex and the data availability is too small, so that the model will simply memorize the data and will try to overfit. So there is always a trade-off between this bias and variance. That is when the ensemble learning comes into picture, but it takes the several classifiers or several accurate and diverse classifiers. So the classifiers has to be accurate in their own space and they have to be diverse so that they can just give different opinions or different predictions on the same data. So when we combine these accurate and diverse classifiers, the resulting prediction is expected to be better compared to the predictions of these individual constituent models. So our current research is focused on combining modality-specific model training and ensemble learning for improving the performance towards detecting abnormalities in chest radiographs. So basically, we aim to transfer modality-specific knowledge rather than image-net knowledge to a relevant target task with an aim to improve the performance in the target task. And also, we aim to reduce prediction variance, sensitivity to the training data, and prevent model overfitting so that we can build robust and generalizable models for real-time applications. Now I'm getting into our studies here at the National Library of Medicine. Our first study, the studies that use ensemble learning and modality-specific training for improving the abnormality detection in chest radiographs. Our first study used a START model ensemble for improving tuberculosis detection in chest radiographs. So basically what we did is we segmented the lung region. So this, I forgot to mention this point. It is very important to segment the region of interest in the medical images prior to doing a classification or segmentation or any task. It's because the regions that do not contribute to decision making may have a serious impact on the decision making process because for example, when you are talking about tuberculosis, it is confined to the lungs, and any region which is outside the lungs may impact decision making. So it's always a wise idea to segment the region of interest prior to doing the classification or any other medical imaging task. So we segmented the lung regions using unit models, and after segmenting the lung regions, we trained a support vector machine classifier using a combination of handcrafted features and deep learning features. We used pre-trained CNNs as feature extractors, and we also used handcrafted feature descriptors like histogram of gradients, GIST, and speeded up robust features, and extracted features from the data and gave those features to the SVM to arrive at the level 0 predictions. The predictions are further fed into a logistic regression-based meta-learner that optimally learn to combine these predictions to come up with a level 1 prediction, and the prediction at the level 1 is found to be superior compared to the predictions at level 0. You can see from the table at the bottom that the E of P1 denotes the performance only with the deep learning based models, and E of P1, P2 shows the ensemble of the deep learning and the handcrafted feature descriptor models. We found that doing an ensemble of handcrafted feature descriptors and deep learning based features gave better results compared to using only the pre-trained CNNs as feature extractors. We also went forward to see whether the model is exactly focusing where it is supposed to. So you can see at the top, the chest X-ray showing an image with tuberculosis manifestations. We found that the model was exactly looking at where it is supposed to. On the bottom image is that of a normal CXR image, and the model did not show any activations. So the explainability of the models, not only at the the quantitative level, but at the qualitative level also carries utmost importance. Our second study is focused on assessing the performance of an ensemble of models towards general abnormality detection. It's not about TB or pneumonia or anything. In general, we wanted to detect the abnormalities in chest radiographs using an ensemble of machine learning models. Here, again, we did an ensemble of handcrafted feature descriptors and classifiers and deep learning models. This time, we used several pre-training models into the process. Like our previous study, where we segmented the lung region of interest and then gave it to several models, including a custom CNN model, a VGG16 and VGG19 model. And for the handcrafted feature descriptors, we used the local binary patterns and histogram of gradients. So once we had the predictions, we used several ensemble methods like majority voting, averaging, and weighted averaging, and we found the best of these ensemble methods. And the best of these methods were used to classify the images as normal or abnormal. In our third study, we performed an iterative pruning of the deep learning models and constructed an ensemble for detecting abnormalities in chest X-rays. We always found that the deeper models are not always optimal, and it is necessary to prune this model at the layer level or at the there are different methods of pruning the models. So in our case, we found that iteratively pruning this model at the layer level gave us better performance compared to using the deeper models as is for doing the classification task. So in this study, what we did is we performed an ensemble of iteratively pruned modality specific CNNs. So the CNNs were trained on chest X-ray data. We have pre-trained them on a very large collection of chest X-ray data to make all the weight layers specific to chest X-rays, and further use them to iteratively prune them to remove the filters with the highest average percentage of zero activations. And then once the pruned models were further combined to ensemble methods using majority voting, averaging, and weighted averaging. In the process, we found weighted averaging resulted in a better performance compared to other ensemble methods. You can see from the table that the weighted averaging of the pruned model was definitely better and it's superior compared to that of the unpruned counterparts. Also, we went forward to visualize these iteratively pruned models and see whether they are able to exactly localize the disease region of interest. The first picture in the leftmost region shows you the chest X-ray with the bounding box annotations, and figure B, C, and D shows the activations of BGG16, BGG19, and Inception V3 models towards localizing the region of interest. You can see that the model is exactly looking at where it is supposed to, and this makes us come to a very firm decision that the model is accurately classifying the image based on disease-specific ROI and not on the surrounding context. Our next study sorry.
Sorry to interrupt you. Maybe because we are running a little bit out of time.
Just 2 minutes. This is the last slide. I'll just finish off.
Okay. Yeah. Thanks. Yeah.
So this study is not only doing the classification at the label level, but also it is doing a localization at. It's also doing an ensemble-based localization. As you can see, we trained multiple models on for the task, abnormality detection task, and we found that multiple models were localizing multiple regions of interest to different extents. So if you can see this rightmost picture, we have multiple models that were just focusing on multiple regions, and we did an localization. We did an ensemble of all these localizations to come up with the final localization. In that way, we found that the ensemble localization gave us better performance compared to the individual localization achieved with the individual models. So these are my publications that discuss all that we have seen right now. And if you have any questions, you can always mail me at rajaramanistu@mail.nh.gov, and all my codes related to these publications are available in my GitHub repository. Thank you very much.
Okay, thank you, Siva, for that excellent presentation. Okay, our next speaker is Dr. Anthony Reina from Intel. He's going to talk about federated learning, a privacy-preserving method for training deep learning methods using healthcare data. This is such a great talk. Yeah, okay, please go ahead.
Oh yeah, sure, absolutely. Thank you for the opportunity. Can everybody see my slides?
Yes.
Oh, excellent. Thanks for inviting me. So I'm Tony Reina. I'm the Chief AI Architect for Health and Life Sciences at Intel. And I work with healthcare companies, primarily medical imaging companies that are trying to optimize their AI algorithms on Intel hardware. Today, I'm going to talk to you about federated learning, which is a privacy-preserving method for training deep learning models using healthcare data. And federated is a really popular topic currently. And so if you haven't heard of it, I think you will within the next year or so. I'm going to try to, in this talk, define and describe what federated learning, or FL, is. I'm going to show you some of the research that I've done on it, and I'm going to point you to the open source federations that we work with. So let's take a step back for a second and just talk about cartoon kind of deep learning, machine learning. Basically, I've got some sort of model at step T. I've got some sort of data that I want to train. It could be MRI, it could be CT, whatever you want. Some question that I want the model to answer. I kind of mix it into a computer, and the computer learns an improved model T+1. But eventually I hit the limit of this data set. Really what's happening under the hood, in one way of thinking of it, is it's learning the statistics of this data set. And eventually the data set, it learns everything that it can about it. So the question is, okay, well, can we just add more data? If I get more data, maybe I can learn more things. Maybe I've got a better distribution. Maybe I've got better statistics now, and maybe I can get an improved model by adding more data. The problem is there's lots of data out there. Hospitals generate oodles and oodles of data, but it's usually siloed. There's usually not a easy way of saying I've got a hospital in Oregon and one in Athens and one in Mumbai, and I want to just share all that data. There's lots of reasons for this. Privacy and legality are probably the first ones people think of. HIPAA, GDPR. Sometimes the data is just too valuable, or the value is unknown. Data is the new oil is the kind of the phrase. And so if you don't know how to price your oil, you're not going to sit there and offer it to people. And sometimes data is just too large to transmit. If you were trying to take all the data from these sites and put them into one centralized site, we could be talking about exabytes of data, and you can't do that. So let me take a step a little bit back and show you one way that we handle large data sets during training. And this will also show you the use case that I do research on. So in my case, I'm using, and Mehul had actually talked about this with brain tumor segmentation. So these are gliomal tumors. There's actually an open source data set called BRATS that we use. MRs of the brain have been annotated by radiologists. And we're basically trying to take a crayon and color in where we think the gliomal tumor is. And we're asking the neural network, the deep learning model, to do the same thing. In data parallel training, imagine we have this enormous data set and we want to go through it fast. It takes a long time to go through millions of images, even though we probably don't have millions of images. But the more images you have, the longer it's going to take. So what you can do in data parallel training is you can shard or break this large data set up into chunks, and you can actually feed each chunk and a copy of the model into, let's say, 3 different computers. And now potentially you're 3 times faster to train this model. So each computer gets a shard, or gets a section of the data, and we train it with copy T, and it gives us T+1 for person A, T+1 for person B. And eventually we have some sort of computer that then takes these 3 versions of the model and maybe does a weighted average or something like that, and comes up with the consensus model at the end. So that's data parallel training. In Federated, we just use the same concept, but if we go back and forth, we're actually saying, okay, the sharding or the separation is already done for us. We have, if this is hospital A, hospital B, hospital C, the data just lives where it lives. It does not move. We're basically moving Muhammad to the mountain rather than moving the mountain to Muhammad. We are making sure that that the data never actually leaves the center, and we're just passing the model to each hospital, letting each hospital train that model, coming up with our now hospital A version, hospital B version, hospital C version, and doing some sort of aggregation, some sort of weighted average to come up with our final model. So back in the Mackay conference in 2018, our group was the first to show that a UNet model, which is a segmentation model that was presented in the last talk, could actually be trained using this. And what we were comparing it to was, in this case, we had actually the original data set, which was open, the BRATS data set. We knew at least that this was hospital A, hospital B. We didn't know what the hospitals were, but there were 10 different hospitals or 10 different shards that we had. And we compared what happens if we use the traditional method of we're just going to train everything as if it were one giant data set, comparing to federated learning. And then we had 2 other techniques, which were essentially kind of like I take the network to one hospital, train it on its data set, take that trained model to another hospital, train it there, and I keep moving the model around from place to place. So we call that incremental learning. you can see that the federated, which is the green curve here, and the collaborative data sharing, or the, if I had access to all the data, actually converged pretty well. The federated learning can get you greater than 99% of the data sharing technique. So again, I never have to actually share the data. I just actually share the model between the different places, and I do this aggregation between these models, and I can come up with a model that performs well on all of this data. We did an update to this in Nature Scientific Reports that was published back in July. So I encourage you to go to this website and look at that paper. We've actually open sourced the code that we used here. There's actually probably half a dozen frameworks that will allow you to do federated learning now. This is our version of it. It's called Open Federated Learning. So we encourage you, if you want to take a look and see what code was used in the Nature paper, you can go here and replicate those experiments. And I want to point out Federated Tumor Segmentation Initiative. So this is actually the original paper we did with University of Pennsylvania, and we've been working with them for about the last 3 years now, and they ended up getting a National Cancer Institute grant for doing a large multinational federated learning initiative, where we've gotten almost 50 institutions worldwide. These are actually these placeholders are actually where the institutions are, to do this glioma tumor segmentation model. And so in the website is called FETS. It's for Federated Tumor Segmentation Initiative, FETS.ai. You can go to this website. We've actually have the code that I showed you before integrated into some open source packages that the University of Pennsylvania does that allow radiologists to basically kind of click a button and make this work on their machine. So this is CapDK, which is one of the open source projects that radiologists can use in the clinic for these federated learning studies. I'm going to stop there and leave it open to questions. I know we just have a few minutes left, but really thank Mehul and the conference for allowing me to talk.
Yeah, thank you, Tony. That's such a great presentation. Okay, I think we can go into discussion, and yeah, please post any questions in the chat, and we'll try to get through as many as we can. Okay, let me get started. Anthony, so if, let's say, this fets.ai, right? Let's say there's a hospital in the US and a hospital in Europe, and they have their own images. So you train the model in US, train it in Europe. You have two sets of weights. How do you combine those weights?
Yeah. So that's a great question. So the first part that this doesn't solve is the annotation part. So you would have to have a consensus annotation. You would have to have a procedure that everybody is going to label the data in the same way. Everyone is actually getting the same copy of the model. So if it's a 3D UNet, for example, in this example, they're actually getting the same copy of the same 3D UNet. So let's say that has 20 million weights. You can think of it as just 20 million numbers, 20 million numbers that each hospital has, and they figure out what's best for their data. If there's 33 hospitals, you have 33 sets of 20 million numbers, and you actually do an element-wise mean based off of it's usually a weighted mean. It's usually weighted by the size of the data that they're contributing. So if they're contributing 50% of the data, they'll be weighted at 0.5. If they're at 25% of the entire data, they'll be at 0.25. There are obviously other aggregation methods that you can use to handle, outliers. What happens if one center is really biased toward, one particular set of weights or another. So you can use medians, you can use harmonic means, you can use all sorts of statistics to combine those numbers together.
I see. And I think there's a question in the chat, how to deal with cases where there is some degree of regional differences. That is, the illness is different in different areas.
Yeah. So that one, I guess it depends on a few things. Number one, the annotation has to be consistent. So if there is a, there are some cases, for example, some data sets even where they have different labels for, let's say, chest X-rays for what's going on, and they could be overlapping labels and things like that. So you definitely have to harmonize that to begin with. The second thing, in terms of just natural differences, if the labels are harmonized, if they're the same, if they mean the same things, that's something that you actually want the network to help to learn. You don't want something that will only, if it's something that works for brain cancer, you're hoping that it's not going to be different in Mumbai than it is in Athens, because theoretically it should be the same brain cancer. Now I can certainly see other diseases having some uniqueness, but for things like this, that's what we're getting at, is to try to take the bias out of the data set by casting this wide net.
Okay, thank you.
I have a question for, sorry to interrupt. I have a question for Tony. This is Shiva here. So you told, thank you. You told that you are going to send the same model to all the institutions. So I have a question here. For example, institution A is going to have 100,000 images, whereas institution B is going to have only 1,000 images.
Yep.
Maybe the same model may overfit for one type of data, but it may underfit for the other type. So in this case, if you should have some kind of a diversity in the model, so that each institution can come up with their own best model, rather than having a fixed model for all the institutions. So what is your take on this, sending a fixed model to all the institutions?
So what we're trying to do is come up with a model that's generalizable. So not one that is overfit for one versus the other. The more basic idea is that you're running in that case, and I couldn't go over it in this talk, but you're getting into IID, so independent and identically distributed distributions. So for example, if you were doing a weather model and you had one center was in Hawaii and the other one was in Nome, Alaska, obviously it would learn different things about the weather because its data set would be biased toward one versus the other. When I went back to this case where I was doing the incremental learning, the actual poor performance here is something called catastrophic forgetting, where you're actually overfitting on, you're moving it from one center to the other, and you're essentially overfitting on that data set, and you can lose information about the previous hospital or the next hospital. And so Federated seems to be, it's not immune to IID or to non-IID, but it is a little more robust because you're actually pulling, you're doing the update at the same time and you're averaging. So if one institution is biased and the other is biased in a completely different way, you're splitting the middle, and you are weighting it according to the number of samples that you see. So it will kind of pull toward the one bias than the other. But you're hoping to split that middle to find the true generalizable model, not trying to make something that only works in Midtown Manhattan.
Thank you, Tony. Thank you very much.
There's a question about using images generated by GANs rather than, or combining GAN generated training data and federated learning, or I don't,
Yeah, you definitely could. So people have been using GANs as a way of generating increasing data set. And so it's definitely done. It really is a delicate thing though. You're essentially having a generator learn that distribution and pull from that distribution some sample that may not have originally existed in that distribution. So if you have a small data set to begin with and it's biased, your GAN is going to be biased toward that. And so you're going to perpetuate that biased over and over again. People do it and it's not wrong. It's just you have to be careful when you do it.
Okay, thanks. Okay,
yeah, Tony, if I can interject, I would say that I think you want as much data from the wild as possible.
Absolutely. Yeah. Absolutely. Yeah. Yeah. Absolutely. Yeah, I agree.
Okay. Next question is for Dr. Stephen Burstenman. How so as you are a practicing interventional radiologist, how does your community take this deep learning? Is it because in the beginning when Jeffrey Hinton had a talk, he said like, we're going to replace all radiologists, right? but we are more going towards like, we're not going to replace them. We're going to help radiologists in their workflow. So I just want to see your take on that.
So it was kind of funny. In 2015, when I kind of started learning about deep learning and realized that, this was real, I was trying to kind of educate people and say, hey, we really should be paying attention to this as radiologists. And all I got was, yeah, whatever. And then with Pranaj and Andrew's paper, all of a sudden people sat up and took notice, and it was very real. Although the initial paper was very flawed, not because the distribution was flawed, but because the Wang chest X-ray 14 data set was very flawed. Just it was a wake up moment. But I think that what we are doing now is that in radiology, we realize that AI is going to be coming. And the question is, how can we use it best for our patients? And, you have to have not only, standards, and not just what the FDA is setting, but you have to have better metrics for evaluation. You have to have better processes for evaluation. You have to have on-site validation, which is extremely important. You can't just take a AI product off the market, put it in to your, hospital and say, we're done, and fire your radiologist. That's not a realistic thing to do. So I think that radiologists in general, we are hopeful that this technology is going to be a good technology, but we are very motivated to make sure it's a very good technology for our patients.
Thank you very much. Yeah, there's another question in the chat about curriculum learning and how it can be used in medical imaging. I'm not familiar with curriculum learning. I don't know if any of you are familiar with
curriculum learning. Was an older Bengio paper, if I'm not mistaken, where you start training, in a piecewise fashion. You add layers. You add complexity to the data. I think it's fine. I think that what's more interesting is the possibility of semantic, developing semantic structures in the data so that we can identify that's a pneumonia, and you have a pneumonia and you have this other area of abnormality. These things together mean something else. I think as a training model, it's fine. I've tried it. I haven't had any real improvement with it. Maybe someone has had a different experience.
If I'm not wrong, curriculum learning is mostly like starting with easy examples and then going for difficult ones. So from the image perspective, like we also do, I don't say it's a curriculum learning, but what we do is we do a progressive resizing of the image. We start training the image with the smallest image size, and then we progressively increase the image resolution, and so as to build up the performance of the model. So yeah, curriculum learning, it's mostly adapted in natural, image processing domain. I don't see much of this being adopted into the medical image domain. So that will be a good one to try, because it's very hard to see what is easy, and so it is hard to distinguish what is easy and what is difficult in medical domain, because everything appears one and the same. As I told you, because of this intra-class variance and inter-class similarity. So the domain matters the most when it comes to going for any type of learning.
Thank you. Okay, another question for Dr. Rajaraman. So, you mentioned like how ImageNet was made on stock images, right? So I know there are some efforts to build like a medical ImageNet. So Stanford has like a collection of images,
yes.
But is there, do you know, in the community, are people building like in normally we have ResNet weights or like ResNet 34 weights? Is there a medical ResNet or a medical like a weight library that's people are working towards? Yeah.
Unfortunately, I don't. I'm not aware of anything as of now, because, for example, Stanford, they came up with their own chest X-ray data called Chexpert, where they have released the Chexpert weights, and people are further fine-tuning these model weights for using this model for any chest X related classification task or something like that. But I don't see any. I don't remember anything at present that comes up with a dedicated model for a chest X-ray or brain MRI or whatever. Like this the Mura skeleton, the Mura data set that classifies the musculoskeletal fractures. I think that one is FDA approved, and obviously they have a well-defined model. But other than that, I don't see anything out right now that can be used with confidence, like the use imagenet models.
Okay, thanks. One more question on federated learning. What are the risks of re-identification? I don't know.
Mm-hmm.
If,
Yeah, absolutely. So there, I wasn't able to go into that, but there actually are papers showing hacking federated learning. So that is part of our research as well. Essentially, somebody mentioned the GAN before. If people aren't playing by the rules, let's say someone is not actually participating in the federation, but is providing updates, they can do a GAN that actually is trying to push updates or models that will cause the other federation members to memorize more of their data to get it right. And in that case, they get the global model and they can invert it and come back. And people have shown this, actually not in medical data, but in image data. This is part of the research. Somebody had mentioned differential privacy as well. There's things like differential privacy, which is one way of working with that. There's also just essentially having ways of making sure that everyone is obeying the rules. There are methods, and Intel has methods where you can make sure that if I'm asking Mehul to run an algorithm that let's say gives me the sum of 1,000 numbers, how do I know that he actually has taken 1,000 of his number? I don't see the numbers. How do I know that he actually did what I asked him to do? There's Intel technology that we have that actually will say Mehul has to give me a receipt that says he has actually done the calculation that I asked him to do with the algorithm that I've asked him to do. So the answer that he gave me should be valid. If that's the case, then it's really hard to get around the federated scheme because there are fewer and fewer ways of hacking it.
Okay, thanks. That's good.
Yeah.
Great. I guess this is a question for Stephen. SPECT imaging generally gets lesser attention from the DL community compared to MRI and PET. Any thoughts about that?
So yeah, unfortunately, nuclear medicine is somewhat unloved, isn't it?
Yeah.
In terms of SPECT imaging, I think that one of the advantages when dealing with SPECT imaging is that you have lower resolution images, and obviously the higher the resolution, the greater the memory requirements, the greater the processing needs. It was only until recently that we weren't really able to make GAN images, bigger than 256 by 256. Mm-hmm. I think it's a great use case. It's a great area for someone to look at. Unfortunately, it's somewhat it's not a very heavily used study. And then the issue being is that there are different radiopharmaceuticals, there are different labels that you're using, and you might have an issue with data from that, or maybe not. It might be summable, and you can going to SPECT CT and go and the other modalities, the extension of the modalities might be helpful. I don't think it's a bad area. I just don't know what the how large it is compared to MRCT and the other modalities that are being investigated actively.
Okay, thank you. I think somebody asked, Joseph asked, what are the hardest problems in medical imaging? Any one of you want to take that? What are the hardest problems in medical imaging?
Okay, so as far as medical imaging is concerned, most of the research is focused on classification and segmentation, and it's beyond that. When it comes to point of care, when we think about a deployment scenario, it's beyond that. So I'm not sure whether the radiologists are really interested in getting to know where the nodule or the tumor is, but they may want to go further in and try to measure the size of the tumor, the depth of the tumor, or maybe the the proximity of the tumor to some other organ, something like that. So I think deep learning is still at the infant level. They are just thinking about segmentation and classification, but we need to go further into how to make these models really useful or really interpretable to help the radiologists or any experts with more in-depth analysis of the problem. So yeah, this is the hardest problem. I don't say it's the hardest problem, but this has not been touched, or it's still at the infant level. So people may have to work on these kind of things to make it happen.
Yeah, I would agree with that. I mean, there's so much metadata that we just throw away, and it's such an opportunity. Once we get segmentation down, we spent really almost a decade, back in the late 90s, early 2000s, trying to do volumetry on organs, and we just kind of got away from it. Now we have segmentation models that can do it easily, and I don't understand why this is not a common thing done. You could just spit out this data with every CT as metadata. There are so many opportunities, and then with that metadata, then we can start mining that metadata, and we can start finding correlations for diseases that we don't even know exist yet. Okay, we can't see the things as radiologists, but it doesn't mean that the correlations are not there. It doesn't mean that a increase in fat in the neck region and increase in perirenal fat, and a certain appearance to the pancreas is a soft marker of impending diabetes. We don't know.
Okay. Okay, there's a question on, the last question is, if someone wanted to connect with the experts, so if they want to connect with Tony, Siva, and Stephen, what's the best way to contact you or connect with you, like Twitter or LinkedIn?
Yeah, for me, I've just given my email ID there in my
Okay.
presentation slides, so they can always contact me in the email ID, and I'll be willing to answer them anytime.
Okay,
Yeah,
thanks.
LinkedIn is good for me. I can.
Okay, thank you. Okay, I think.
And for me, Twitter or LinkedIn.
Okay, sounds good. I think that's all the questions, and yeah, we are out of time too. So I want to thank all the speakers. Thank you so much for doing this. This really benefits the community. And thanks to Sam and Mia and all the organizers for helping us set up the session.
Thank you, Mehul. Thank you
Mehul.
for all the organizers. Thanks for making it happen. Thank you.
Yeah.
Thanks a lot. Very enjoyable session.
Great, thank you everyone. Thank you Mehul, Stefan, Siva, and Tony. This was a great session. And thank you everyone for attending. We have a related session coming up on Friday called The Fundamentals of Medical Image Processing for Deep Learning. And Nareej Sharma will be giving a technical presentation about processing medical images stored in DICOM format before passing the data in deep learning algorithms. So if you like this session, be sure to check that out. That's Friday, 10/23 at 9:30 a.m. Pacific. Once again, thank you so much to our panelists. This was great, and have a great one, everyone. See you soon.
Yeah, thank you.
Thank
Bye.
you. See you. Bye.